I'm going to present to you the work I've been doing during my PhD at the Laboratoire de Physique de l'ENS under the supervision of Jean-Pierre Nadal. So this work has been done in collaboration with Jérôme Sacure and Jean-Denis Martin for the experimental part. And I would like to start by thanking Laurent for all the help during the project. So first, I'm going to start with a small introduction about what is perceptual decision-making in the context that I will be using. So what I consider perceptual decision-making in this talk is simply a visual discrimination. So for example, a visual discrimination task can consist in a choice between different categories. For instance, if you look at the following picture, one question you could be asked is if it's a cat or a dog. So in this case, I'm guessing everyone will say that it's a cat, and your choice between the two categories is easy. But sometimes choice can be a lot harder, like this picture, where it's not that clear if it's a cat or a dog. And so this kind of choice between categories occurs during the everyday life, when we work, when we do some tasks. But this is not exactly the kind of perceptual decision-making we can control with an experimental setup. Well, I'm going to present the specific task that we used in order to study perceptual decision-making in this visual discrimination context. So the task is the following. So participants, which were human, look at the screen, and after a small delay, they will see some circle in gray here with some bars. So we call this a Gabor patch. And the bars have an orientation, which can be clockwise or anti-clockwise. And depending on the orientation, it's more or less easy to decide if the orientation is clockwise or anti-clockwise. So the goal of the participants is to report their decision, so clockwise or anti-clockwise. And after having reported this decision, they have to report their confidence in this decision on a scale like this one, from 0 to 9. So 0 meaning that they consider that their answer was completely random, and 9 meaning that they are absolutely certain that they had the correct answer. So if you consider this kind of perceptual decision-making task, of course, you expect to have different relations between the reaction time of the participants, how much time did they need in order to report their decision, their accuracy, how much time were they correct in reporting their decision, their level of confidence, for example, or even the difficulty of the task. So here, it's a few examples of the relations we can find in the different behavioral variables of the decision-making task. Each panel represents a participant. The y-axis represents the response time of the participant, and the x-axis, the reported confidence of the participant. You can see two things. First, every participant has a different range of response time. Like it can go as fast as 400 milliseconds, and it can go to like almost, no, even like 1.2 seconds for some participants. But there is one thing that all have in common, is that the response time is a decreasing function of the confidence, which makes sense because if your confidence is high, that means you are almost certain that you had the correct answer. Your decision had to be fast because that more or less means that it was an easy decision for you. And if we look at the relation between accuracy and confidence, this time we find the opposite relationship, with the accuracy being a monotonic function of the confidence. And when your confidence is high, the accuracy is almost at 1, meaning like you never guess the wrong answer. And this again makes sense because if your confidence is high, you have more chance to be correct. So The next part of my talk will be to try to explain briefly the models that we can use in order to reproduce this decision-making behavior. And these models have been based on some neuronal data. And now we are going to compare them to behavioral data. So the class of model I consider is called attractor model. It consists of two neural populations in blue and red here. And each population represents one of the two categories. For example, the blue will represent bar oriented to the left and red bar oriented to the right. So these two populations are selective for one of the two decisions. And so they are going to receive an input that depends on the difficulty of the task. For example, if the task is very easy, both populations are going to receive almost, no, sorry, if the task is really hard, both populations are going to receive almost the same input. At the contrary, if the task is very easy for, let's say, the left decision, then the current IL is going to be a lot greater than the current IR in order to reflect this difficulty of the task. Now, in order to have some dynamics for these two neural populations, we need to connect them in a specific way. So the neurons within this population exhibit self-recurrent excitation. This is in order to have a dynamic that is self-sustained, meaning that it does not relax to zero just like that. And to reflect the decision-making process, we have inhibition between the two neural populations in order to have competition between the two possible decisions. Now, if I consider this kind of network, and now I send a specific stimulus, so consisting of the currents IL and IR, I'm going to observe a specific decision-making process, which is the following. You can see that this process can be more or less divided into parts. In the first part, the firing rate, the RI, of both units in blue and red are more or less the same. And after a small amount of time, one of the two firing rates start to increase and win the competition because like the difference between the two firing rates is big. And what we are going to say is that we are going to say that the decision happens when one of the two population, so here the blue, reaches a decision threshold theta. So in this case, the network has chosen the orientation left. There is only one small issue with this kind of model, which is that they are called attractor because you more or less reaches an attractor state in order to perform the decision. But if I go back at my experimental setup, it's a sequential setup, meaning that the typical time course is the following. You look at the first stimulus, you perform your first decision, and then after some waiting time, you are going to see a second stimulus, and you are going to perform a second decision, and so on and so on. But that means that for the attractor model, you need a way to be able to relax between the first decision and the presentation of the second stimulus. Otherwise, you will be stuck into the previous attractor corresponding to the previous decision. So if you are able to introduce a relaxation, and that's what we did, then you are going to obtain the following kind of dynamics during the whole time course of the decision-making task. So first, you present a first stimulus. Then you have a competition between the two populations. And so in this case, population blue won the competition here. And as it won the competition, you have a relaxation of the dynamics towards the resting state. And thus, at the presentation of the second stimulus, the network is able to perform a new competition in order to perform a new decision. And so in this case, the red population has won the new competition. So I have more or less shown that attractor neural networks can perform sequence of decision making, sequence of decision trials. And I'm going next to use it in order to describe the experimental setup I described at the beginning. So to do that, I need to fit the attractor network. And we are going to assume that this fit can be done. I won't have time to present how to do it. But the main idea is that you fit the parameters of the network on the mean reaction time and on the mean accuracy of all the participants. And if you do so, you obtain the following result. So this is for the confidence experiment, or the confidence of the experiment where participants report their confidence. Each panel, again, represents a specific participant. The x-axis is the angle of the orientation, so it's related to the difficulty of the task. And on the left, you have the response time with respect to this angle. In red, it corresponds to the experimental data point, so the experiment. And in blue, it's the results of the model. So you can see that the model is able to capture the whole variety of response time for all the participants and the relation with the difficulty of the task. And it does the same thing for the accuracy with respect to the orientation, like on the right. So it's the same, you have different shape of accuracy with respect to angle, and the model is able to capture that. So these attractor networks can be fitted on behavioral data. But in the previous, like in the experiment I presented, participants were not just doing a simple decision-making task because they had to report their confidence. So the next step is to find a way to model confidence within an attractor neural network. To do so, I come back to like one typical time course of the dynamics of my network during the decision trial, which was the following. And you can note that once the blue population, so the winning one, reaches this decision threshold theta, you have a specific difference of activity between the winning and the losing population. Because of the stochasticity of the dynamics, this difference is not going to be the same for all the trials, depending on the difficulty of the task and other parameters. What I'm going to say is that the reported confidence of the participant is simply a function of this difference of activity at the time of the decision. So if I make this hypothesis, then what I want to do is, starting from my histogram of delta R for all my simulations, I want to find the function f that map this histogram onto the reported confidence histogram, which come from the experimental data. So, for example, this function f can be obtained using like an histogram matching procedure. And if I do so, I obtain the following thing. Here, each panel represents a participant. And in blue, you have the experimental histogram of the reported confidence. And in orange, you have the histogram of my network, meaning after we applied the function f to the difference of activity. So you can see that it works pretty well. Model and experiment have the same distribution of histogram. But most importantly, this function f is different for every participant because we can only do this procedure for each participant separately. But if you look at the function f for every participant, it always has the same shape. So here, in the x-axis represents the difference of activity at the time of the decision. And this curve here represents the function f that is obtained through the histogram matching procedure. And the dash line in light blue for every participant represents a fit by a sigmoid function. So you can see that every participant, despite the specificity of their response time, accuracy, and confidence histogram, the mapping from delta R to the reported confidence is always done using a sigmoid function. So there is some kind of a common thing between all the participants, even if they don't have the same histogram confidence histogram. So there is only one small issue with this method is that so we have fitted our network on reaction time and accuracy. And this confidence is obtained through with a mapping from simulation to experimental. So in order to decide if this modelization is accurate, we need to test this model of confidence on data. And so to do so, we need to check if the relationships between reaction time, accuracy, confidence are present in the model the same way they are present in the experimental data. So here, it's the same figure as at the beginning, but I add lines, and the lines represent the numerical simulation using the model for the reported confidence. And so you can see that despite not being fitted on confidence, the attractor network is able to reproduce the relation between response time and confidence, both qualitatively and quantitatively. And despite the fact that all participants have different relationships. And if we look at the relation between response time and confidence, it's the same. The attractor network is able to capture this relation. And again, because that the model was not fitted on this data, meaning that the fact that it reproduces this behavior means that this modelization of confidence has a chance to be accurate. And so to conclude this talk, I'm going to recall the three main points. So first, attractor neural networks that comes from the study of neuronal data can be fitted to behavioral data of individual participants, which means they are not just correct to explain neural behavior. They can be used to explain more cognitive behavior of participants. And they're able to explain a lot of behavioral variables like confidence, response time, accuracy, difficulty of the task, and all the relations between all of these variables. And the last point, I didn't have time to present it here, but it's an important point because, of course, attractor models has a specific dynamics, which is nonlinear, as you have an attractor state. And what I showed PhD was that this nonlinearity is essential to explain a lot of effects that are observed in decision-making experiments, such as, for example, if you perform a decision, like you choose clockwise on your previous decision, then on the following decision, you are going to have the tendency to choose clockwise again. You have some kind of repetition effect. And so the nonlinearity of attractor model is essential in order to reproduce this various effect in behavioral experiments. And so with that, if you have any questions.